Students, this is the first video on steam power plant cycle. Okay? Right. So first we will see what is the steam power plant, what are the main elements of the steam power plant, how they function. Okay? Now, basically steam power plant consists of 4 elements. So boiler, turbine, condenser and pump. So out of these 4, we already discussed in details about the boiler and condenser. Okay. Now, here in next coming semesters, you will study about the turbines as well as the pumps. Okay. Right. Now, so as we know, in boiler, we are converting the water into the steam by exchanging the heat. Okay. So boiler is a steam generator. We can call boiler also a steam generator. In the boiler, the water is converted into steam by using the hot gases. Okay. Now that steam generated in the boiler is going to expand in the blades of the turbine. Thereby, the shaft of the turbine rotates. Okay. So as we know, the application of the steam is to generate the power. Therefore, we are expanding the steam in the turbine. Thereby, the shaft of the turbine rotates. Okay. If you see, this is the generator. The shaft of the generator is also coupled with the shaft of the turbine. Means whenever the turbine rotating, the shaft of the generator is also in rotation. Thereby it produces electricity. That electricity we can transmit with the help of the transmission lines. Okay. Now after the expansion, so in the turbine we know the steam is expanded till the condenser pressure. Okay. Right. Now this steam is discharged into the condenser, thereby using the cooling water or feed water, converting the discharged steam into the feed water, and that feed water again we are feeding into the boiler. Okay. So means these are the 4 elements of a steam power plant. Okay. Now we will see what is the basic cycle for this steam power plant. Okay. So for any engine or cycle, the basic cycle is the Carnot cycle. Okay. As we know, in Carnot cycle, there are 4 processes, 2 isothermal process and 2 adiabatic process. Okay. So isothermal compression, adiabatic compression, isothermal expansion and adiabatic expansion. Okay. So that Carnot cycle will give good results when it is operating between 2 fixed temperatures, that is source and sink. Okay. Right. Now, the Carnot cycle is not a suitable model for the steam power plant. Why? Because if you remember, you already studied in engineering thermodynamics psychrometric chart, right? Now, you can see here, this line is the saturated liquid line and this line is the saturated vapor line. Meaning that it is the state is liquid on this line, the state of the substance, and the state of the substance on this line is the vapor. Okay. Now, at this point where this saturated liquid line and the saturated vapor line are intersecting, that is the critical point. Above that, it will behave as an ideal gas. Okay. Means left of this line will be liquid and right of this line will be vapor. And in between we have 2-phase mixture, that is the liquid plus vapor. Means point 1 state is pure liquid, point 2 state is vapor, and 3 and 4 are combination of liquid plus vapor. Okay. Now we got this one, liquid line, vapor line, and critical point. This is a critical point and it will behave as ideal gas. And this is the 2-phase mixture, that is a combination of liquid and vapor. Okay. So as I mentioned, the Carnot cycle is not suitable for a steam power plant. Why? Because, so first one is, we are expanding the steam in the turbine, right? That is till to the condenser pressure. Okay. Now, if you expand to the lowest pressure, what will happen? So inside the turbine and water will be formed. So that water will corrode the blades of the turbine. Okay. That is the first problem. Due to the low quality, it will erode the corrosion, we can say, corrode the blades of the turbine. And it is impractical to design a compressor that handles 2-phase, meaning that now here you can see 2 to 3 is the expansion of the steam in the turbine and 3 to 4 is the condensation, then 4 to 1 is the pumping the water into the boiler now, right? So at point 4, what is the state? It is liquid plus vapor. We don't have any device to pump a combination of 2-phase mixture. That is a combination of liquid plus vapor. So that is the reason it is difficult. Okay, it is difficult to pump the 2-phase mixture. Okay, that's what it is difficult. It is impractical to design a compressor that handles two-phase mixture. Okay. And next, one more difficulty is it is difficult to control the condensation process that precisely has to end up with the desired 0.4, right? So it is not possible to stop at 0.4. Okay. So these are the problems with the Carnot cycle. The Carnot cycle cannot be applicable for the vapor cycle, right? So there are certain changes are there in Carnot cycle. So if you make changes, then we can call that as the Rankine cycle. Okay. So even in Rankine cycle also we have 4 elements. So we have boiler, turbine, condenser, pump. Okay. So pump is the work consuming device because it is used to increase the pressure. That's why we are adding work input to the pump. And in the boiler we are adding the heat, thereby it is converted into the steam. And in the turbine we are getting the work, output. In the condenser heat is removed. Okay. Right. So now this is the simple Rankine cycle. So we'll discuss what is process 1, process 2, process 3 and 4. 1, 2, 3, 4. Okay. So basically Rankine cycle consists of 4 processes similar to Carnot cycle. So here isothermal processes are replaced by constant pressure process. Okay. So the difference between Carnot cycle and Rankine cycle is in Carnot cycle isothermal processes are replaced by the constant pressure process. Okay. Now, so first process 1 to 2. 1 to 2 is the compression. You can see one is here, 2 is here. 1 is before the pump, 2 is the after the pump. Means 1 to 2 we are pumping the water. We are increasing the pressure of the water to the boiler pressure. Means during this 1 to 2, what we are doing? We are adding the work to the pump. We are giving work input to the pump. Okay, that's what. Water enters the pump at state 1 as saturated liquid and is compressed to the operating pressure of the boiler by isentropically. Isentropic process is also called as reversible adiabatic process. Okay. Now, so now 2 to 3. 2 to 3. This is entry to the boiler is 2. Exit from the boiler is the 3. 2 to 3. What we are doing? We are adding the heat at constant pressure. We are adding the heat at the constant pressure. Okay. So that's what 2 to 3 is the constant pressure heat addition process. Here the saturated water enters the boiler at liquid phase and leave it as a superheated vapor at state 3. Means for the boiler, entry is the liquid state, exit is the vapor state. 2 to 3. Now 3 to 4 is the expansion of that superheated steam inside the turbine. 3 to 4. Okay. At 3 it is entering, at 4 it is leaving. Okay. So that is the isentropic expansion. Superheated vapor expands isentropically in the turbine till the condenser pressure. Okay. Till the condenser pressure. Then at 0.4 the exhaust stream from the turbine is entering into the condenser and at state 1 it is leaving. Okay. So 4 to 1 is the constant pressure heat rejection process. Okay. We are exchanging the heat from the exhaust stream to the condensate liquid. Okay. High quality steam is condensed in the condenser. Now you can see in TS diagram, as I told, this black line, this is a saturated liquid line and this is a saturated vapor line. And you can see this line inclined horizontal again. This is called constant pressure line. 2 to 3 line is called constant pressure line. On this line, wherever you pick a point, at that point pressure is constant. Got it? So the starting from 2 to, if you go like this, this line is called constant pressure line in cyclometric chart. So on that line, at any point, if you pick a point, there the pressure is constant. Okay. Now you can see 1 to 2. 1 to 2 we are adding work to the pump, thereby the water is raised to the boiler pressure. Now 2 to 3. Now you can see 2 to 3. This is the constant pressure line. During that process we are adding the heat, thereby the water is converted into the steam. Okay. Now 3 to 4. 3 to 4, it is the expansion process in the turbine. So in that the turbine is producing the work. Okay. We are coupling this shaft to the generator shaft, thereby we are getting the electricity. At 0.4, you can see 0.3 is above the vapor line. Okay. It is the superheated. So this is, it is 100 degrees vapor line. This is superheated vapor, 0.3. Now 0.4 is the vapor. Okay. At 0.4 it is entering into the condenser. Now if you see 4 to 1, it is the condensation process. If you go through the Carnot cycle, where is the 0.4 after condensation? What is the point? Where is the point? It is a two-phase mixture. But here after Rankine cycle, after condensation, the point is on saturated liquid and it is a single phase mixture. Okay. So therefore it is easy to handle the single phase mixture. Okay. That is the reason the Carnot cycle is not applicable for the steam power cycles. Okay, so isothermal processes are replaced by constant pressure process. That cycle is called Rankine cycle. Got it now? Now, so 1 to 2 is the work done on the pump, and 3 to 4 is the work done by the turbine. 2 to 3 is the heat added to the boiler. 4 to 1 is the heat rejected from the condenser. Okay. Now, if you analyze the energy equation, right? So, you already studied about steady flow energy equation, right? What is steady flow energy equation? Total energy plus heat addition is equals to total energy plus work done, right? So, you can define, say, enthalpy plus internal energy, right? Okay, plus Q is equals to enthalpy plus internal energy plus the work done. Okay, so the total energy is constant indirectly, steady flow energy equation, right? Now, if you apply it to the pump, so right, in the pump it is let us say isentropical process. There is no heat addition or deletion. Therefore, Q is equals to 0 for the pump. Therefore, at state 1 it is entering, at state 2 it is leaving. But where the enthalpy is more, at point 2, because the temperature is more, right? So therefore, work done on the pump is equals to difference of the enthalpy, that is higher enthalpy minus lower enthalpy, that gives the H2 minus H1. Okay, this is the work done on the pump. Now, coming to the boiler, we are adding heat to the boiler. Okay, some 3 to 2. Okay, at 2 heat is added, at let us say 2 is the starting point, 3 is the ending point. Okay, so where the enthalpy is more, at the exit only always, right? So H3 minus H1 gives the amount of heat added. Again, in the boiler there are no moving parts in the boiler, so therefore we can assume work done in boiler will be 0, because in the absence of moving parts, work done equal to 0. Therefore, heat added is H3 minus H2. Now again, turbine is insulated one. It is okay. It is isentropic expansion. Q is equals to 0. Okay. So then work done by turbine is equals to, at 3 it is entering, at 4 it is leaving. Where the enthalpy is more, 3 only, because the temperature is more. Okay. It is a superheated steam, and this is only saturated steam. Okay. Because the point 4 is on saturated vapor line. Therefore, enthalpy is more at point 3. Therefore, H3 minus H4 gives the work done by the turbine. Okay. Now, fourth one is the condenser. In the condenser, there are no moving parts. Therefore, work done is equals to 0. And it is used to remove the heat from the system. Therefore, Q out is equals to higher enthalpy is 4 and lower enthalpy is 1. H4 minus H1, right? As we know, thermal efficiency is equals to work done by heat supplied. Or we can say that net work by heat supplied. What is net work? Net work means out of the work produced by the turbine, certain amount of work is consumed by the pump. Therefore, net work is equals to turbine work minus compressor work. Turbine work minus compressor work gives the net work divided by heat added. Heat addition is in the boiler. If you substitute, you will get the thermal efficiency. Okay. So, in terms of enthalpies. Okay. Now, you can see you will get enthalpy. H1 is the enthalpy of water at P1, and small v, you can say the pump work is also calculated as specific volume into pressure difference. H2 minus H1 is also equivalent to specific volume into difference of the pressure. So, you will get 1 minus TL by TH, the enthalpy, 1 minus T2 by T1 in terms of Carnot cycle, if you want to say. The thermal efficiency is 1 minus T2 by T1. Okay. So, this is the ideal cycle. But actual cycles are deviated because of the isentropic, due to the friction. Okay. So, due to loss of heat to the surroundings, the actual system is not always obeys the ideal system. There are such small differences are there. Okay. So, the deviations of actual pumps and turbines from isentropic ones can be accounted for by utilizing isentropic efficiency. So, thereby we can define, because they are deviating from actual cycles, ideal cycles. So, therefore, pump efficiency can be defined as isentropic work to the actual work, and turbine is the actual work to the isentropic work. Because the pump is a work consuming device, therefore it is defined as the isentropic work to the actual work, and whereas coming to the turbine, it is a work producing device, therefore actual work to the isentropic work. If you see the TS diagram, instead of 2 is the actual one, but 2S is the isentropic one. Okay. So, therefore, now efficiency of pump is equals to H2S minus H1 by H2 minus H1. That's what isentropic work to the actual work. H2 nothing but H2A. Similarly, turbine, instead of 3 to 4 is the actual process. 3 to 4S is the ideal process. H3 minus H4A by H3 minus H4S. Okay. So, this is the efficiency of the turbine. Okay.